Okay, hi everyone. So this is a chapter 10 lecture on stoichiometry. Let's go to the slides. So chapter 10 is on chemical calculations and chemical equations. And our first topic, equations, stoichiometry. So stoichiometry, you can think of it as a recipe. It's just a fancy word for a recipe, right? Just like you would have a recipe in the kitchen to make dinner from a set of ingredients. In chemistry, it's the same thing. Your set of ingredients would be some molecules, some chemicals that you mix together, and then the result is a product, right? So it's the same thing. How much of one thing that you mix with another, right, is what's called a recipe, right, or a stoichiometry. So if you look at this equation, for example, 4NH3 plus 5O2 goes to 4NO plus 6H2O. The way you can think about it, again, as a recipe, right, is that you need 4 molecules of ammonia and 5 molecules of oxygen gas to form 4 molecules of NO gas, nitrogen monoxide, and 6 molecules of water, right? Normally we would scale this up because we're thinking in moles and not molecules, but it's the same idea, right? So 4 moles of ammonia makes 4 moles of nitrogen monoxide, right? So you can think of it in any way, you can couple any of the reactants and products. For example, you can say 5 moles of oxygen gas will make 4 moles of nitrogen monoxide. You can say 5 moles of oxygen gas will make 6 moles of water, right? So you can relate things just like in the kitchen, you say, okay, I'm going to need 3 eggs to make 1 omelet, right? Or I'm going to need, you know, uh, 6 cups of water to make chicken noodle soup, right? So it's just a recipe, and it's based off of the conservation of mass. So if you can see here, if you take the molar mass for each of these compounds and then you multiply it by the coefficients, you'll see that the reactants have the same mass as the products due to the conservation of mass, right? So that's where it comes from, right? Both sides will have 228 grams. Okay, so now when we go and do stoichiometry calculations, that's all we have to keep in mind is reading a balance equation to let us know how much of each thing we need to make a product. And so those types of calculations are called stoichiometry. So let's keep going with our kitchen analogy, right? Making things in the kitchen to illustrate how stoichiometry works. Let's say you want to make a sandwich and you want to make a ham sandwich. And what you require to make a ham sandwich is a piece of ham and 2 slices of bread to make 1 sandwich, right? So here you can see that we have 1, 2, 1 as our coefficients for the balance equation, right? You have 2 pieces of bread on the left side. You have 2 pieces of bread on the right side. You have 1 slice of ham on the left side and 1 slice of ham on the right side. So this is a balance equation, and it tells you, right, what needs to go together with what to form that product. Okay, so now using this balance equation, we can answer such questions like, how many ham slices are used when 6 sandwiches are made? Now, I bet you guys can do this really quick, right? We make 6 sandwiches, then we're going to need 6 ham slices, right? And we only know that because we know how many ham slices is needed to make a sandwich. So that's 1 ham slice makes 1 sandwich. We call this the mole-to-mole ratio, right? It's 1 to 1. 1 ham makes 1 sandwich. Okay, so we are using that mole-to-mole ratio, which actually we talked about in a previous video, right? The mole-to-mole ratio. It's the same one here, except in this case, you're using the coefficients of the balance equation to get your mole-to-mole ratio. Okay, we can answer the second question. How many bread slices are used up when 6 sandwiches are made? Well, for every 1 sandwich that's made, 2 bread slices are used up, right? So if you're going to make 6 sandwiches, you're going to need to use 12 bread slices, right? So because it's 2 to 1, okay? So the mole to mole ratio this time is 2 to 1, right? And you guys are all doing this in your head, right? Which means you are able to understand what stoichiometry is. Now, of course, when we switch over to chemical equation problems, the numbers are not going to be so pretty, right? You're not going to be able to do it in your head. But you know you would know the method in which to do it is by using the mole to mole ratio, right? And so that's why we're doing this analogy. So you can see that actually it makes sense, right? It's intuitive. You guys actually already know it. Okay, so let's do the third question. How many bread slices are used up when 6 ham slices are used up? Okay, so now this question is asking a slightly different thing, right? It's asking about relating 2 reactants together. So you can do that as well. We don't always have to think in terms of sandwiches, right? Now we're thinking in terms of bread and ham. So if 6 ham slices are used, right, that means 12 bread slices must have been used because it's a 1 to 2 ratio, isn't it? So for each 1 ham slice, 2 bread slices are used. So if you use 6 ham slices, you use 12 bread slices, right? Fourth question, how many ham slices are used up when 8 bread slices are used? Okay, again, we are doing a 1 to 2 ratio. If 8 bread slices are used, just divide that by 2, right? So that means 4 ham slices must have been used. Okay. All right, so now I can show you guys what are the basically what we're thinking about when we're answering these questions, right? How do we actually calculate it? Because when you get to chemical formulas, like they're not going to be such nice numbers for you guys, right? And so you're going to need to know how to set up the problem. So this is how we've been setting it up. You start with what you're given, which is 6 sandwiches, okay? Then you need a conversion factor. And this conversion factor is basically your mole to mole ratio. So you're going to have 1 ham slice on top, because that's your desired unit, to 1 sandwich on bottom, right? Because you're relating sandwich to ham. So 1 ham slice on top, 1 sandwich on bottom. Sandwich will cancel out, and you have 6 slices, right? 6 ham slices, okay? In the second question, how many bread slices are used up when 6 ham slices are used up? Well, start with what you're given, 6 ham slices, and now do that mole to mole ratio between bread and ham again. So you're gonna have 2 bread slices on top, 1 ham slice on bottom, and you're gonna get 12 bread slices, right? Okay, so now let's switch over to like a real chemical equation and see how we deal with that. So right now we have 2CO plus 2NO goes to 2CO2 plus N2. First, make sure that it's balanced, right? That's the first thing before you do any calculations is make sure that it's a balanced equation. So we got 2 carbons on each side, 2 nitrogens on each side, 4 oxygens on each side. So we're good. Okay. And then the question asks, how many moles of N2 are produced when 3.5 moles of CO reacts? Okay. So notice in all of these stoichiometry problems, like you're only asked to relate 2 things at a time. Okay. So in this question, find the 2 things that you're relating. Okay. Here's N2 is one thing, and then asks you to relate to CO, which is the other thing, right? That means you can ignore NO and you can ignore CO2. You only care about the coefficients in front of N2 and in front of CO. That's all you need to get the mole to mole ratio, okay? So that means if I have 3.5 moles of CO, I'm going to want to put mole of N2 on top because that's what I desire, right? And so there are 2 conversion factors here that relates CO and N2. One where moles of CO is on top, one where mole of N2 is on top. So of course you want to pick the one where mole of N2 is on top. and moles of CO is on bottom. So that moles of CO will cancel. And what we get is 1.75 moles of N2, right? So we're effectively taking 3.50 and dividing by 2, okay, to get the 1.75. Now, you don't have to memorize that, right? You don't need to memorize when you need to multiply or when you need to divide, as long as you use the method of unit analysis that we've been doing. Make sure that the desired unit is on top, and you're going to get your answer, right? Okay, and now this makes perfect sense, right? Because if you look at the ratio, for every 2 CO that's reacted, you form 1 mole of N2, right? So it's 2 to 1. So now if you have 3.5 moles of CO, well, you're going to get half of that, right? Half of N2 is going to come out. So what's half of 3.5? It's 1.75, right? So makes perfect sense. It's intuitive, right? And really, it's foolproof if you just have a balanced equation. Find A and B, right? So A here would be N2, and B would be CO, right? Find your 2 things, A and B, and then do the mole-to-mole ratio. Right? Okay, and so this is a part of the roadmap that I've already showed you guys. This format, right? I've shown you guys the roadmap before. Let's review it, but this is very useful in stoichiometry. So have that handy, right? Whenever you're solving these types of problems. Now you can start with, particles of A, so either atoms or molecules of A. Using Avogadro's number, you can get to moles of A, right? And then with molar mass, you can convert mole of A to gram of A, right? And then there's the other side, the B side, right? To go from A to B, if you're asked to relate A to B, that's when you know you need the mole-to-mole ratio. And that comes right here, right? Mole-to-mole ratio, where do you get that? From the equation coefficients. So going from mole of A to mole of B, you're going to use that mole-to-mole ratio, and you get over here. Now, the B side is going to mirror the A side, right? So for moles of B's, you can get to grams of B using the molar mass of B. Or you can go to particles of B using Avogadro's number, right? So this roadmap that we've seen before is going to be in play here for solving stoichiometry problems, right? So in these types of problems, always figure out which box you're going to start at, right? Maybe you're given grams of A and you're asked to go to grams of B. So then you'll put your finger on grams of A and you map out your path. Okay, I need a molar mass to get to moles of A, and I need to get to moles of B using mole-to-mole ratio, and I need the molar mass of B again to get to grams of B. Right. And you guys are so proficient now going between moles and grams, so that should be easy. The only new thing here is you're gonna be doing the mole-to-mole ratio. Right. That's the only new thing. Okay, so let's do this example problem. How many moles of NaCl, or sodium chloride, result from the complete reaction of 3.4 mole of Cl2? Okay, I'm actually going to do this on the board for you guys, so it's easier to see. Copy down the equation first. Okay, and notice how the question is phrased as well. So that you can pick up that, oh, okay, this type of question is a stoichiometry question. So I use my roadmap. I use mole-mole ratio, right? So how I see it, right? It's always going to be asking about amount of something resulting from something else. So it's just like in the kitchen, right? How many buns do I need to make 10 hamburgers? Right? So it's that type of question, just with chemicals, right? Instead of food ingredients. Okay. So anytime you see that line of questioning, you know that you have stoichiometry, and you're going to use the roadmap to solve that kind of problem. So you're always going to start with what you're given, right? Here's the balance equation. We check quickly that it's balanced. Yes. It's asking how many moles of sodium chloride. That's our product now, right? That we can get from reacting 3.4 moles of Cl2. Okay. So you start with what you're given. 3.4 moles of Cl2. You'll draw that line. That's going to be your mole-to-mole ratio, right? That's your conversion factor. Now, look at the two things being related. Obviously, Cl2, right, and NaCl. So you completely ignore this. You don't care about that, right? Remember, it's always two things at a time, not more than two. So it's really easy to see which two coefficients you need. You're going to need a 1, you're going to need a 2, okay? Now, the next step is which one goes on top, which one goes on bottom? Well, the one that's desired, right? We want mole of NaCl out. So the 2 is going to go on top, 2 moles of NaCl over 1 mole of Cl2. Okay, that's an implied 1 up there, right? So as you can see, then your mole of Cl2 can cancel out, and you're going to get 6.8 moles of NaCl, okay? Which makes perfect sense, right? Because for every 1 mole of Cl2, you can make 2 moles of NaCl. So if you have 3.4, you're going to need to double that, right? But notice, if you just set up your conversion factor right, the multiplication and the division, whatever it is, it's going to work itself out. You don't have to do that thinking, right? That's why it's such a foolproof way of solving problems. So 3.4 times 2, 6.8, just because the 2 is on top, right? And again, where does that come from? The coefficients. And why is it called a mole-to-mole ratio? Because it's literally a mole-to-mole ratio, right? 2 moles of A, 1 mole of B, right? So we're going here, and that's that part of your roadmap is going from mole A to mole B. Okay. All right, let's go back to the slides. Okay, let's do this one. According to the following equation, how many moles of water are made in the combustion of 0.1 mole of glucose? Okay, so we'll do it on the board. I'll just copy down the balance equation. Asking how many moles of water so can be formed from combustion of 0.10 mole of glucose. Okay, so we start with 0.10 mole of glucose. And glucose is C6H12O6, right? It's kind of obvious here what glucose is because that's not glucose, that's not glucose, that's not glucose. So it must be C6H12O6. Okay, then we draw that line. We got to figure out what the mole-mole ratio is and which one's got to go on top. Okay, so where's our A and where's our B? Well, you can call this A, you can call it B. It does not matter which one you call A or B. You just need to know that there are two separate things that you're relating. So you're relating this one and you're relating that one. That means you can ignore this, right? So you're only concerned with the coefficients in front. And since we want water out, because the question, right, is how many moles of water? So you're going to want to put a 6 mole of water on top and the 1 mole of C6H12O6 on bottom, just like that, right? So it turns out it's a multiplication, right? 0.1 times 6 is 0.6. 2 makes 0.60 moles of H2O. Okay. Pretty simple, right? All right. Okay, so now we're going to expand it. So the last two problems we did, we just went between mole A and mole B on your roadmap. Now we're going to do mass to mass conversion. So we're going to start at grams of A, and then we'll end up at grams of B. So this problem says, how many grams of glucose can be synthesized from 58.5 grams of CO2 in photosynthesis? Okay, so I'll write the equation on the board again. And then we'll solve it. How many grams of glucose? How many grams from 58.5 grams of CO2. Okay, so again, when we have a bigger problem like this, I would write a plan first before you start solving. So use your roadmap to come up with the plan. Okay, so the plan is going to be, okay, where do we start? We start with what we're given. We are given what? Grams of CO2. So that's grams of A, right? Put your finger on grams of A. Now, the only road you can go from grams of A is to mole, right? And you're going to quickly realize this, is that all of these chemical stoichiometry problems, the first thing you need to do is get things to moles, because chemical reactions, that's how they react, is in mole and not in gram. So anything that you're given, you're probably going to have to go to mole, right? Because only when you're at mole can you cross that bridge to the other side from mole A to mole B, okay? So that's something that a lot of beginning chemistry students ask me is, when I'm looking at these long problems, how do I know where to start and where do I go next? Well, you start with what you're given, and where you go next is likely mole, okay? So that's mole of CO2. And now you're at mole A, right? Now you can cross over because it's asking about something else, right? It's asking about B. So you know you need to get to mole B. In that case, mole B is the glucose. But it doesn't want it in moles. It wants it in grams. So you know that you need one more step to convert mole of glucose to gram of glucose. Okay. So get that plan first. That's going to help keep you organized. And then you start your problem solving. So you start with what you're given. Now it's 58.5 grams of CO2. You need to get to moles of CO2, right? How do you do that from grams to mole? You guys are experts at this now. Molar mass, right? So you do 1 mole of CO2 on top. Then 44.01 grams of CO2 on bottom. 44.01 is the molar mass, right? Remember, molar mass is in grams per mole, okay? Okay, so we wanted mole on top, right? That's why we end up dividing 44.01. Now we get to the next part, mole of CO2 to moles of glucose. That's A, that's B, right? So go to your balance equation, put your finger on CO2, put your finger on glucose, and look at the coefficients, okay? We want glucose out, right? The question is asking for glucose, so we want the 1 mole of glucose on top. And we want the 6 moles, right? The 6 coming from the coefficients of CO2 on bottom. Okay. So now we're there. Okay, and the next step, we need to get from moles of glucose to grams. So again, we need a molar mass, but this time we need the molar mass of glucose, right? Quite big, six carbons, 12 hydrogens, 6 oxygens. Let's calculate that. Get my calculator. Okay, so it's 180.16 grams per mole. Since I want grams out, 180.16 grams goes on top. And 1 mole goes on bottom. All right, let's punch that in. Three sig fig, so 39.9 grams of glucose. Okay. All right, so let's recap here, right? Write a plan first using your roadmap, and then you execute with the numbers. What you notice is the mole to mole ratio comes in the middle, right? You get to mole first. The mole to mole ratio is from the balance equation, it comes in the middle. And then on both sides, you need the molar mass, right? And notice that the first round, you divide by the molar mass. And then to get to grams of B, you actually multiply the molar mass. right? So that's sort of how it's always going to be when you're doing the mass to mass conversion. But you don't have to memorize this again, right? You just need to set it up so that your desired unit is on top. Right. Okay, let's go back to our slides. Right. Okay, let's do this one. A mixture of hydrazine, which is N2H4, and hydrogen peroxide is used as a fuel for rocket engines. These two substances react as shown by the chemical equation. N2H4 plus 2H2O2 goes to N2 plus 4H2O. And then it asks, how many grams of H2O2 are needed to completely react with 50.0 grams of N2H4? Okay. So again, let me write balance equation. We'll do this on the board. All right. So again, how many grams of hydrogen peroxide will react with 50 grams of N2H4, right? So that's our two things we're relating now. That's our A and B. Equation is balanced, right? Always quickly check. So first step, make a plan, right? Where do we start? Grams of hydrazine, so grams of N2H4. So put your finger on that on your road map. The only road you go to next is mole, right? The only road points to moles. So you're going to convert to moles of N2H4. Now you're at mole A, right? And it's asking for what? Grams of B, right? So put your finger on that as well. Start at grams of A, go to grams of B. So the next thing to get to grams of B is you need to get to mole of B first. So mole of H2O2, okay, before you can get to grams of H2O2, right? Again, if you have that roadmap in front of you, super easy, okay? So we start with what we're given, which is 50.0 grams of N2H4, okay? And then we need to get to mole, so we need the molar mass of N2H4, right? Let's quickly calculate that. So 32.05 grams per mole. We want mole on top, right? So 1 mole of N2H4 is 32.05 grams of N2H4. Okay, so that cancels. Now we're here, right? We need to go from mole N2H4 to mole of H2O2. That's going from mole A to mole B. So put your finger on N2H4, H2O2, and look at the numbers in front. We want moles of hydrogen peroxide out, so we need the 2 on top, 2 moles of H2O2, okay, to 1 mole of N2H4. So that will cancel. Now, last step, we need to get to grams of H2O2. So we're going to need the molar mass, right? Go to mole to gram. So you're going to have 1 mole of H2O2 on bottom now, right? Because you want grams on top. So let's figure out the molar mass of H2O2. It's 34.02 grams per mole, right? Grams per mole, okay? So moles of H2O2 cancels, okay? And then what do we have? (106 grams of H2O2. 3 sig figs, right? Because of that number. Okay. So notice, similar to the previous problem that we did, right? You first divide the molar mass, right? Then of A, then later we multiply, right? Nothing that you have to memorize, as long as you just set it up with the desired unit on top using our method of unit analysis. Okay, let's do one more problem. How many grams of O2 can be made from the decomposition of 100 grams of PbO2? And there's your balance equation, which I'll write on the board. And it even gives us the molar mass, which is nice. Okay, so the question is, how many grams of O2 can be made from 100 grams of PbO2? Okay. All right, so again, our plan. Start at grams of PbO2, right? That's grams of A, and we're asked to get to grams of B, right? Here's A, here's B. So, right, on your roadmap, you gotta get to mole first. Mole of PbO2, that's moles of A. Then you go to mole of B, and then you go to grams of B. Okay. Then we execute 100 grams of PbO2. Give us the molar mass. This is grams per mole. We know we want mole of PbO2 on top, right? That's the desired unit. So 239.2 grams of PbO2 on bottom. Then going from mole A to mole B, got to use the mole to mole ratio from the balance equation, right? We want mole of O2 out, so that's going to go on top. So look at the coefficient there. That's 1 mole of O2. And then on bottom, it's going to be 2 moles of PbO2. Okay. And then to get grams of O2, molar mass of O2 is 32 grams per mole. So 1 mole of O2 on bottom, 32 grams of O2 on top. So what we get is we got 4 sig figs here, so 6.689 grams of O2. All right. So I've done 3 of these problems for you guys now. As you know, I always say I can do 10 of these, but it's not going to help you until you go and like knock them out for yourself, right? So go and practice, grab some problems from the book, or just Google them and start practicing these stoichiometry problems. Okay, so that's it for this video. I'll see you guys in the next one.